All right, good morning. March 6th, 2025. Elec 13, 25 winter network cabling class. Fancha College. All right. That's for all those introductions. And today we're going to talk about the category cabling. So let's see if I can come up with some beautiful intro. It should fade in. All right. Ooh, yeah. There's category cabling. All right. You know what I mean by category cabling. Sometimes you hear the term Cat 3, Cat 5, Cat 5e. The Cat stands for category. So let's take a look at some of the aspects of what makes it a category cabling, and about the specifications of specific cables in specific situations. All right, so this is not a picture of Ethernet cables. It's actually coax that I took from one of the local facilities, at one of the local facilities. If it were Ethernet cable, what's wrong with this picture right away? I just wonder if anything stands out when it comes to this picture. And if not, I will tell you. Anybody first see anything that just jumps out right at you with this installation? No. Okay, that's fine. That's why we are in school. Look at this here. See those bindings right here? See how they bite into the cable? Not a bite into the cable, but they deform the cable. The bundles are kind of squeezed by these bindings. Thin wire, is it a zip tie? Are they zip ties? Maybe they're zip ties. Or maybe they're just those twisties from local grocery store. Probably not. All right. That would be a no-no with Ethernet cable, because Ethernet cable is very sensitive to any deformations, any sort of deformations. When we are giving you the labs to do in class, and when we are terminating anything that has to do with the Ethernet cable, we are stressing out that the twist has to be kept right to the connection point. That's one. Two, there should not be any squeezage going on, squeezage of the cable. So squeezing the cable, deforming the cable, bending the cable too hard or too much, and for sure stepping on it, or if sometimes it pulls out of the box, and we had that yesterday in our lab. The cable was pulled out of the box, and whoa, there was a bit of a knot, and that created a kink. Kinks are not really good news when it comes to Ethernet cabling. Yes, sometimes it happens that, when it comes to Cat 5e, you can just straighten out the kink and massage it out a little bit to kind of make this thing so like nothing happened. Cat 5e may forgive you up to some point that kind of abuse, but Cat 6 will not. Cat 6, even if you step on the wire, you are changing the physical aspects of it enough to cause problems when it comes to the data transfer. Yeah. All right, so we should not be using zip ties when bundling or wire managing. When we talk about wire or cable management, we should not be using zip ties when it comes to Ethernet. Yes, then somebody might ask, okay, what did we just do yesterday during our labs? Yes, we have used zip ties in a small kind of configuration, but what did I tell you? I told you not to squeeze that, not to bind it too hard, just provide a kind of like a running guidance. The wires should be just kind of sitting there freely. All right. Now, why is it that sometimes you're going to have a complete zero tolerance policy about not using zip ties when it comes to Ethernet cables? It is because some people know what to do when using zip ties, and some people don't know what to do. Sorry to say that. Okay, so if there's a boss in the company or a supervisor, they are not going to kind of categorize people. Oh, this person knows how to bind the cables. This one, okay, so you know what? All across the board, no zip ties. Because I can use a zip tie here and there with category cable, but I know how to use that. And yes, some people might get up in arms. No, no, it should be never used. Yes, you are also correct, but I am also correct. I'm giving you enough info, educated, so you can make an educated decision of what to use and how to use it. But it's also safe to assume a policy that no zip ties with Ethernet cables. What do we do? Okay, there was a question there. What do? We use Velcro. All right. And not only we use Velcro, we use that Velcro soft side in. If you flip it around, nobody's gonna die. But just to be on it, even more precise, soft side in. And here are a couple of pictures showing Velcro. You can buy Velcro in bulk and just have it in your toolbox. Excuse me. Or you can just buy some smaller, and sometimes it comes with just like a thin strip, and sometimes you get the thicker strip. So, yeah, Velcro comes in different shapes. Really good idea to have a roll of that in your stash. And this is how we bind it, how we bind the cables. Two things I'm going to tell you about this image. First of all, right here, somebody did that wrong, but I kept the picture because I'm telling you soft side in, and over here somebody did that. It's a picture from the internet. Here's a source. Somebody did that soft side out. Not too much of a big deal, but if we want to do some rules, let's stick to the rules. Also, what we have here, another thing I'm going to point out. See this bundle here, how it goes. Those cables in this bundle are, you could say, run in a messy way. That could be done on purpose. So there are two schools, quote unquote schools. Run the cables, all the cables nice and beautiful, so you can trace every single wire with your eyes, and they're nice and combed nicely, so you can just see like a beautiful type of a bundle with all the wires straight, and every wire has its place and it runs in a straight line. That's one school. The other school is run it in a messy way, and the reasoning for that is crosstalk. And I'm going to come back to that. Well, this question of how to run the cables which way, it's going to be probably unsolved till the end of the world and one day longer. But we're going to come back to this picture when we go along with our slides here. Just want to make sure that we're not running out of time. All right. So here is the more overlays of the text. Now, here is a concept. All right. Let's say that this is a conductor, a piece of wire. a section of it. It continues somewhere to that side, and it continues somewhere towards that side. It's a single happy conductor. Let's say if we introduce an electric current flowing this way here, and let's assume something that's called a conventional current flow, which in conventional current flow, the assumption is that the current flows from the more positive to the more negative side of whatever it is, as opposed to electron flow. When it comes to conventional current flow or electron flow, if you assume any of that convention when you do the calculations, your calculations are going to end up correct as long as you maintain the convention from the beginning to the end. So if you start your calculations in conventional current flow, go all the way and finish them in conventional current flow. Same thing with the electron flow. If you start, then you have to carry through and finish all your calculations in electron flow. But all right, so there is a current flowing through this single happy conductor that we have on the screen. What is going to happen when we have electricity or electric current flowing through a conductor? We have something like a magnetic field happening. We have electric field that points with, as the arrow does right here, and we have magnetic field. So we have electromagnetic field. The magnetic field is the one that spins, and it spins in this way here. So if it's a conventional, there we go. I lost my mouse for a second. If there is a conventional current flow, just imagine a corkscrew. When you turn the corkscrew this way clockwise, it advances into the cork of the wine bottle or the bottle of wine. Then this direction of the corkscrew moving could be the current, and the turning, the direction of turning into order to advance that, it will be the direction of the magnetic field spinning or rotating. All right, so what happens if we introduce another conductor that is just a passive conductor, not connected to any sort of power supply? We could have that thing connected to a resistor, so there should not be any electricity or electric current flowing through that, because this passive cable that was just put in proximity here has no power supply to provide the electric current. All right. So what is going to happen? If that cable or the conductor, is brought close enough to the active conductor that actually has a current flow, the magnetic field is going to embrace both of them. If that conductor finds itself within the magnetic field, then we can induce a current flow, because the current flow causes magnetic field to spin, and the spinning magnetic field is going to cause the current in the other passive conductor, providing that there is a change. So it's not going to work in a DC environment. However, if you have an AC, which is the alternating current, then you are going to have electricity induced in this passive conductor. That's how transformers work. We can use that to our advantage. And sometimes we don't want that thing to happen, but it happens anyways. Okay. That brings us to the idea that is called crosstalk. In electronics, Crosstalk is a phenomenon, any phenomenon by which a signal transmitted on one circuit or channel of a transmission system creates an undesired effect in another circuit or channel. The voice that, for example, that I'm speaking with, if you graph that on the oscilloscope, it is not going to be a straight line. It is going to look like an AC, or alternating current, alternating voltage. Well, the condition for the current to start flowing is that the magnetic field has to change. With any change of magnetic field, there's going to be current induced. So my voice is always changing, always changing, always changing. So there's a bunch of changes. On those bunch of changes are going to, if this magnetic field is strong enough, it is actually going to cause electric current. So my voice from this line, if that conductor is carrying my voice, can actually bleed through induction into the other conductor. Sometimes it is called bleeding through, crosstalk. Okay. Crosstalk is usually caused by undesired capacitive, inductive, or conductive coupling, which is joining. Now you might want to research those if you want, but if you want to know more, and if you're too lazy to research, and if you have time, I'll spend extra time with you to explain those things. But this rabbit hole never ends, like when it comes to knowledge here. All right. So crosstalk is usually caused by undesired capacitive, inductive, or conductive coupling, which is joining from one circuit or channel to another. It's basically a signal bleeding through from one pair to another. In structured cabling, electromagnetic interference, or magnetic field interference from one pair to another, because we use pairs for communicating in an analog form. Crosstalk analog. Let's say we have a happy kind of couple of people having a beautiful, nice, and happy conversation on a telephone. And their telephones are connected with a wire. I'm not sure if you can see that here. And there is another conversation happening between two other happy people, which are having another happy conversation. And somewhere along the line, those wires run together over a certain type of distance. Well, that crosstalk can happen between those two wires, between those two conversations, that these two people might actually hear those two people's conversation. It was a very common problem, a common occurrence, sometime, up till maybe mid-90s or so, where telephone lines were way more popular than the POTS telephone lines. That's all we had almost, with some cellular communication, some cell phones, but it was very, very at the beginning stage. Now everyone has a cell phone, so that crosstalk is not really an issue right now. However, if there was, telephony is not the only signal transferring situations you're going to encounter. So I just want you to, using telephones as an example, right? So the problem was that you'll be talking on the phone with someone, and somehow all of a sudden you can hear some other conversation fading in. You can hear two people talking. And sometimes it will be so strong that if you speak, they would hear yours. Sometimes you would just like you will hear them, but if you talk to them, they will not hear you. The crosstalk would be sometimes funny ways. It would manifest itself in funny ways. But that's what crosstalk is. Now that's an analog. In analog configuration, in analog system, why am I? Oh. Huh. My mouse is behaving funny. I'm sorry, I apologize. In analog situation, crosstalk can be annoying. You could hear other conversation bleeding through your through your conversation, and if it there used to be that TV stations would transmit through antennas, and most people would just see receive the cable through receive the TV signal through antennas. And sometimes when you were close enough to one station, one transmitting station, and close enough to another one, somewhere in between, depending on which one is stronger at the moment, sometimes you would see the football game or something like that, and all of a sudden you're going to see another signal kind of superimposing, kind of trying to bleed in through that through the air, and you're going to see some sort of like a ballet performance, so that could be annoying, right? The stronger signal would win, but if it was just a interference, you would see your main channel interfered with some other channel. It would be annoying to you, but still you would see who won the football game. Now, when it comes to digital, story is different. Let's see if I can bring up my board. Come on, board, be brought up. All right. Let's say we get a main signal with analog. Here is a sine wave of analog. Looks like waves. And then if there is another weaker signal that gets superimposed into that, you're going to see both. You're going to see the main thing and some of the bleed through signal, the interference. That's analog. It will be annoying. Okay? Analog. Right. Analog. Can't type. Crosstalk. All right, let's draw a line separating the two situations. And let's have a digital crosstalk. What happens with the digital crosstalk? My text. All right, digital crosstalk is something. It's a little bit different. Now, when you have a digital signal being transmitted, it looks like this here, and like that, and like this. So all that signal, and then it's going to be divided into sort of like time slots, okay, equally spaced. This one is not equally spaced. All right. Now those equally spaced time slots are going to be also implemented on the receiving side here, equally, So let's say during this first one, you get 1 because the signal is high. Right? During the second one, looks like you're going to have a 0. During this one here, well, let's say there's another one here, okay? So here's 0, here is 0, here is 1. Let's say here is 0, and here is 1. So the signal, the receiver, if it's going to be synchronized in a way that is going to read the signal at the same speed, because you can't fully synchronize the receiver and the transmitter because it takes time for the signal to travel from the transmitter to the receiver. And it takes, well, milliseconds, sometimes even seconds. And the signal is kind of in microseconds type of a speed. So what happens is that at the beginning of a transmission, the transmitter is going to say, and now. And the and now is going to travel, and it's going to get to the receiver, and the receiver is going to say, and now, okay? It's going to receive that, and then it's going to start reading at the same speed that this thing is being transmitted. It's called baud rate. So then it's going to receive, right? This one first, that one first, then the second, third, and so on. So it's going to, at the end, it's going to receive 1, 0, 1, 0, 0, and 1. Okay. It's going to get the message through. If you interfere with that by introducing an interference signal that is going to be maybe some sort of, I don't know, maybe even could be a analog kind of waveform transformer or fluorescent lights going on, producing interference, alarm cable, systems cables, they're very noisy. Then at the transmitting side, or even through the medium, if it's a cable here, and if the interference goes through the cable, it's going to mix in with those. So when the receiver starts reading, it's going to read not what was transmitted, but it's going to have extra, maybe 0 and 1, 1 here, 0, 1. So it's going to receive completely different, something different. And in digital, the messages are important, what the ones and zeros are. That's basically what it depends on. So the transmitter is going to say, nope, this is something that this information makes no sense, and I'm going to shut down the receivage of the signal. I'm not listening to you. So the transmission is going to fail. Differences between analog situation and digital transmission, analog transmission, digital transmission, interference can be annoying, and sometimes the stronger signal can take over if the interference signal, if the interference signal is stronger than the original signal, is of course then the receiver is going to lock on to the interference signal, so if the other channel is stronger. But for the most part, it will be annoying because you're going to have some other signal cutting through. But you still will be able to receive that. It's just the quality of the transmission is going to go down. In digital, when crosstalk happens, the transmission completely fails. It just goes. And over here, if you watch that video, it's what is it, 3 minutes? There's a person showing the digital interference or digital crosstalk by folding a cable a certain way. It is an extreme situation because when you see the bunch of data cables, they're running beside each other in bundles. So you're going to say, okay, what gives? What's happening here? I thought we were not supposed to have. That's an extreme situation that this person is showing, and it is possible. Now, so that's why, before we continue onto the UTP, when we're bundling the cables, sometimes you want to have those cables bundled nicely so you can just see every single cable. And when you look at this, you see a bunch of cables like that, and they are nicely bound by Velcro and so on. So there are a bunch of cables run. That's one of the schools of installations. The other school says run the cables as they go, so they might actually, be run in sort of like a purposely messed up way. What is the idea behind that? The idea behind this whole thing is that when you have a signal going, it's going to cause maybe some magnetic field spinning, and if the cable is straight for long enough distance, and if there's another one beside it that is also straight for long enough distance, that can affect the other one, and the crosstalk can happen between data cables, which might end up in loss of transmission. That's the logic behind that. Over 30 years, I never had that problem, and most of the time I was doing things this way because the neatness of the installation. And there's another reason why I did that, and I'll show you, and I'll tell you in a minute and a half. All right. Now, when you have the cables run in sort of like purposely disorganized way, then there will be some magnetic field here, some magnetic field here. They won't have enough carry-through power to cause interference because they're going to be a little bit here and then it's going to disappear, a little bit there maybe. It's not going to have that accumulative power to interfere from one pair to another. Okay, but here is it would be simple if things would be simple if they were simple, right? The problem with this one here, with this situation, to me, now, I never had an interference problem, but I heard somebody that I know really well, that's also in business, over the 30 years, once they had that problem. Now, the problem I have here is a little bit bigger problem with this unorganized sort of purposely bundle. When you bundle cables, the pressure of the cables that are inside the bundle, they're being physically pressured by the cables that are surrounding them. And the bigger the bundle, the bigger pressure once you get towards the middle of the bundle. And if there is a wire kind of crossing another wire, and if that wire presses on the other one, you are going to create an indentation in the cable. It's like a micro band. Two types of bands usually apply to fiber optics. If you run a cable around the corner of a building, that's a macro band. If you have a cable sitting in the tray, and if you accidentally put something on top of that cable, you're going to create an indentation on that. So that is that's a micro band. So you could create a bunch of micro bands which are going to affect the specifications. You're going to change the specifications of the cable. It's just like tying it with zip ties and squeezing them hard. It's just like stepping on those wires when they're on the floor while they're being pulled. So I gave you this the two situations, and I gave you the reasoning. Of course, when you get yourself hired, if you get the job in this type of field, you're going to assume the policy of whatever your company's policy is, and you're going to do it as your boss tells you when it comes to that kind of stuff, because the boss signs your paycheck. Can you refuse some work? You should refuse some work, even if it's your boss, if you see that something is going to create a danger, pose any kind of hazard. Then yes, you have to refuse the work. Hazard to yourself or hazard to others. Other than that, here, you do as your boss tells you because the boss signs your paycheck. If you do this job on your own, if you own the company, then you can come back to this lesson and you can decide. You're going to have an educated decision to make of which way you want to go. All right, UTP stands for unshielded twisted pair. And that's what it looks like. Now, I haven't stopped talking about those straight or messy bundles because we're continuing the reasoning for that too. So keep that in mind. We can tell that this is Cat 6 cable. How can I tell that this is a Cat 6? It has that separator. See that insert separator inside? Cat 5e doesn't. All right. We have 4 pairs: blue, orange, green, and brown. And the pairs are twisted. And the whole cable is unshielded. There's no foil surrounding it or any kind of a braiding going on. And the pairs are twisted. What's the reason for the pairs being twisted? The pairs are being twisted so the magnetic field doesn't have enough constant accumulative power to affect the other, because if there was a straight wire, the magnetic field would be nice and uniform and it can easily induce electricity flow in the other pair. But if you twist that pair, then sometimes the magnetic field is going to point this way, sometimes the other way, and it's not going to have, as I say, accumulative power to affect the other pair. On top of that, you could see that each pair is twisted at a different rate. So there's even less chance of the accumulative power of the induction happening. Now, that's what Cat 5 would be, or Cat 5e. Cat 6, on top of that, again, has a separator that each pair has its own little kind of a groove to be in, and that separator along the way is twisted. So there's even less chance of the magnetic field accumulating and affecting the other pair. So you decide if that is what's happening here, and if you put this cable beside another cable that also has that kind of arrangement, what are the chances of 2 pairs aligning in a perfect alignment out of any bundle that the magnetic field would actually be strong enough? Because those pairs, that whole twist, the orange pair from one and the orange pair from the other one, will have to align perfectly. They will have to align perfectly, plus the rate of that twist also has to align. So chances are slim that this is going to, 1 in a million, could be. So I'm not worrying as much about making those wires nice and neat, not to cause the interference. For me, it's more important that those cables in the bundle do not physically cross each other and not causing the microbands. Unshielded twisted pairs, this is just to show that the pairs are twisted at different rates. The purpose of the twist is to eliminate the crosstalk between pairs, and actually that twist idea was thought of by no other than Mr. Alexander Graham Bell some years ago. So that's not a new idea. Shielded twisted pair. That's what it looks like, more or less. You have tin foil surrounding every pair, in some cases. And then you have the grounding cable, the grounding conductor that basically runs along. It's bare wire. The grounding cable or the conductor has to be connected as per instructions. So sometimes you want to connect that in one end only, sometimes you want to connect the other end only, and sometimes you need to connect that at both ends, usually at both ends. Although UTP cable is the latest expensive cable, it might be susceptible to radio and electrical interference. It should not be too close to electric motors, fluorescent lights, etc. In presence of high interference, shielded twisted pair might have to be used. If you are connecting modules or running data wires in the industrial setting, like where the machinery is with a lot of electric motors, then you will have to use the shielded pair. If you see any modules connected in the industrial environment, you will see shielded pair, shielded twisted pair. The shielded twisted pair can come as follows. Shielded twisted pair is available in 3 different configurations. Each pair of wires is individually twisted with a foil, or there is a foil or braid, just there is not each individual one, but there's one foil that grabs them all, surrounds them all as a group. Or sometimes when you need really, really good protection, you wrap up the cable comes in a way that each and individual pair is wrapped, and on top of that there's one main one that wraps them all. Now, CCA in our case stands for copper clad aluminum, or aluminium if you're in UK. If you magnify the conductor, that's what it looks like. There's aluminum, it's coated with copper clad aluminum. Those cables, those data cables or any other cables, when it says CCA, they're about 3 times cheaper than the BC, which is bare copper, which is the whole wire is copper. Even though it's 3 times cheaper, do not buy that CCA. You see the CCA, you run from it as far as you can get. It only causes trouble. That's all I can say. Do not be tempted because of the price is good. Make sure if the price can be good, just make sure it's not CCA. The wire breaks, doesn't make good connections, and as you go along, it causes connectivity problems. And physically, actually, the physical structure of that is weak. It breaks very easily. So I wouldn't even take that cable if somebody was giving it to me free, because you can't even take that to the junkyard because they don't want it. Now we're going to finish on this table. We got about 2 minutes. We should 2 or 3 minutes, we should be enough with that. Here's the categories of the cable. Cat 5, it's not used anymore, but we also have Cat 3, but it's also not used, obsolete. But still being used sometimes, not in data world, but maybe in intercom or some kind of control signals or whatever. But we're talking about the data here. So Cat 5, Cat 5e, Cat 6, all right? We keep going like that. Right? Here's the gauge. You see Cat 5 as gauge. The conductors are the gauge 24. Look, we go Cat 6, the gauge kind of goes 23, which means the wire is thicker. Right. And here is the twist rate. Cat 5 has some significant twist. Cat 5e, tighter twist, and you can see as we go along, the twist gets kind of tighter. And here is transfer speed and the bandwidth. Transfer speed and the bandwidth. Transfer speed is expressed in bits per second, not bytes per second, bits per second. Transfer speed, the speed is bits per second, never bytes. Storage is in bytes, but it's not per second, right? It's just bytes. But speed is bits per second, and this one has, Cat 5 has the transfer speed up to 100 megabits per second, which means that the signal can be transferred at that rate, and still the cable is going to carry that signal to the other end as long as it's no longer than 300 feet, and the signal is still going to be usable and understood. And here's the bandwidth for analog transmission. What kind of analog carrier frequency you can shoot through that cable, and that frequency is not going to be aliased or otherwise destroyed. Applications, pretty much obsolete, not used anymore, Cat 5. But you can still see it there, right? Now, in the Cat 5 case, the transfer speed is equal to the bandwidth. Well, they just have the same numbers, 100. And this is in hertz, bandwidth in hertz, because it's analog type of thing, right? It's almost like a radio signal. It is like a radio signal or carrier. All right, Cat 5e. Same gauge, a little bit tighter twist. Oh, transfer speed, way more. From 1 megabit per second to 1 gigabit per second. Whoa, that's a lot faster. You can transmit data through Cat 5e. That's why a VoIP telephone system will work on no less than Cat 5e. Cat 5, you can see some old installations still being there. That cabling has to be replaced if you want to install the VoIP telephone, for example. Maximum length, again, 300 feet. And here's the bandwidth. That's why I showed you that slide to explain what CCA is. The bandwidth of that, 100 megahertz, which is analog kind of a signal that it can carry. 100 megahertz with CCA and 300 megahertz, 350 megahertz with bare copper. Applications, Ethernet networks, home, small offices, commercial. Cat 6. Now, the cable, the conductor is thicker. The twist is tighter, and you could tell that it's Cat 6 because you're going to see that separator here. Where were we? Cat 6. All right. It can carry 1 gigabit per second, so no change with Cat5e. Again, the distance 300 feet, and here's the bandwidth with CCA and bare copper. CCA, don't even use that. I'm showing that because it's listed, but I would never ever install CCA cable anywhere. But look here, Cat6 can carry 10 gigabits per second, but only up to 180 feet. So, if you are designing a system and the client says, oh, is Cat6 better than Cat5e? Well, yeah, but, okay. So yeah, even if we have to pay more money, can we have Cat6? Well, okay, let me see your facility. Let me see your building. Let me see your scenario, situation. Let's see how long your runs are going to be. And the run is, remember, it's not just a straight line because you have to go 10 feet up in the air, then whatever the distance, and 10 feet down from the ceiling. You have to account for that. And maybe you're going to have a service loop here and service loop there. So the distance adds quickly. So if the distance between the one end of the link, maybe at the LAN room location, and the desktop location, if it's more than 180 feet, then the client pays for nothing. Might as well get Cat5e because after 180 feet, the speed drops down to 1 gigabit per second. The network interface card sometimes is going to sense how fast it can send, and it's going to switch modes automatically. Then there's Cat6a, thicker cable, heavier cable, more difficult to install, more difficult to run, takes longer to put them on the jacks, and the jacks are way more expensive. But if you want to get up to 300 feet and with the full benefits of Cat6, which would be 10 gigabits, then you should get Cat6a. A stands for amended and E stands for enhanced. Both of those kind of mean enhanced. Okay. So I'm not going to go down to the table because now you know how to read this table. All right, hold on. But also, as the technology advances, by the way, I also saw, over 30 years, I was never aware that Cat6e exists, but it does, because I saw it with my two own eyes. Right? I didn't put that in the table. Maybe I'll find the specifications for Cat6 to see between, because see kind of what is the difference between where would Cat6e fit with the specs between Cat6 and Cat6a. But I know it exists. And as the technology advances, there is another cable, because you can see here, Ethernet doesn't go any longer than 300 feet. 300 feet is the most distance you can cover with Ethernet cable. However, there is a new cable that just came out, well, maybe a year ago or something. And correct me if I'm wrong, but this is 2025 right now. We're talking in early March. That cable is called a game changer. The name of the cable is actually, the cable is actually called a game changer, and it is a game changer because the way it is constructed, somehow, I don't know what they did, that the engineers were able to accomplish, that they came up with a cable which is Ethernet cable that can go up to about 1,000 feet. So it is a game changer. And it is called a game changer. I keep asking around some of my friends that still are in the business on a daily, day-to-day business within the infrastructure, data infrastructure, and I haven't seen people. They have seen the cable, but they have not implemented any installations yet with that game changer cable. But I can see that if you can go by with the cable the 1,000 feet, in some cases you will have to use that if you want to maintain the standards of speed transfer or bandwidth. Okay, so we're going to finish on this. I'm going to stop at this slide, and next week we'll continue. And on sometime tomorrow, I will release test number 2, which is going to cover what I told you. And I just don't want to put that on YouTube here because years from now the information will not matter. But look at the course plan that is published for our year, for our school, and it's you're going to see when the content is, what and when the tests are. Right. So this is it for today, and I will see you when I see you. Some of you in the labs and some of you in the theory class still this week. All right. Thank you for your attention and have a wonderful day.